Hi everyone. In this lecture, I'll start with the analysis of the step response of first order RL circuits. Since I've already done how to analyze the step response or how to draw the step response of first order RC circuits, RL circuits is not that difficult, but for the sake of continuity, I thought I'll discuss some problems on RL circuits. So first we'll start with a simple RL circuit of this type, and I'm applying a step input going from 0 to Vx volts, and you're supposed to plot the output across the inductor. Now we know the instant, in this lecture, I'm going to assume the initial voltage or the initial currents through the inductors is 0. Okay, this analysis assumes that there is no initial conditions in the circuit. So this is more of a forced response. So I'm applying a sudden step input at the input, where the input voltage goes from 0 to Vx, and you are supposed to plot the voltage across the inductor. Now we know that to analyze this in time domain, you just need to know three parameters. So V0 of 0, V0 of infinity, and the time constant. Once you know these three, you can very easily draw. In fact, the first order step and impulse responses can be easily drawn by the knowledge of these three parameters, step especially. Now first, the instant you apply the input, inductor is going to behave like an open circuit, so the input voltage is entirely going to appear across this. So V0 will be equal to V0 of 0 will be equal to Vx, and in the steady state, the inductor impedance is going to be 0, and a current of Vx by R will be flowing in the circuit. Okay, so we can simply, so V0 of infinity is going to be 0, the inductor impedance is 0, it can carry a finite current with 0 voltage across it, and the time constant is simply L by R. It's a first order circuit, so L by R is the time constant. So you're going to start from Vx, and the output is going to decay down to 0 with a time constant of L by R. Okay. Now when I replace the inductor with a resistor, I just interchange the resistor inductor positions. Now in fact, in the same circuit, I'll just go back to the first circuit. In the same circuit, if I ask you to draw the waveform of the current, now that you know the voltage across the inductor, you have to simply integrate the voltage with respect to, use the equation 1 by L integral V0 of t dt will be nothing but the current through the inductor. So I can use that and compute it, or we can just use a simple first order analysis. The instant you start the circuit, inductance is going to behave like an open circuit. So therefore, the current in the circuit is going to be 0, because you will have a resistor and an open inductor, and this node voltage with respect to ground is going to be Vx volts. So you are going to start with a current of 0, and in the steady state, inductor is going to behave like a short circuit, and the current built in the circuit is going to be Vx by R. Again, it's a first order system, so you will start from 0 and approach it asymptotically with the time constant of L by R. Okay, I am not writing the mathematical equations for this. We have already done it extensively in the previous lectures. So this lecture, I thought I'll very quickly browse through all the problems, okay, on first order RL circuits. So now in this circuit, if you are asked to find the step response for this circuit, instantly you just need to find first what is the initial value, V0 of 0, that you find when there is a sudden step event. At that point, inductor will behave like an open circuit, so the current in the circuit is 0, so the voltage across the resistor will also be 0. And in the steady state, what happens is that the inductor will behave like a short circuit, so Vi will be equal to V0. V0 will be equal to Vi. So in this, Vi of infinity will be equal to V0 of infinity, which is Vx. So the time constant is L upon R. So again, this is a standard predicted response. You are going to have input raising from 0 to Vx with a time constant of L by R. Okay, so now I'm going to take a little bit slightly more complicated circuits, but nonetheless the procedure is very similar to analyze. Okay, so again, this circuit has two inductors, but we can see that, let's say this is the voltage Vi, and V1 be the voltage across the inductor and V2 be the voltage across the second inductor, there is a linear relationship between V1 and V2. Okay, so the moment there is a linear relationship between the voltages of two inductors, then the order is going to be less than 1. It will be reduced by 1. So the maximum order can be 2, but here the system order is going to be only 1. Okay. Now you are supposed to draw the step response where the input is going from 0 to Vx volts for the circuit. Now first, the instant you apply the input, we know that you have to find V0 of infinity and V0 of 0. So V0 of 0 is the instant you apply the input, inductor is going to behave like an open circuit. So the circuit simply reduces to R and 2R. So you are going to start from 2 by 3 Vx. Okay, and V0 of infinity is going to be steady state voltage where the inductor impedance will start dominating. Okay, whenever you have an inductor and resistor in parallel, in the steady state or for DC values, inductor will dominate. So the circuit will reduce to L and L. So the gain in this case is half. So the final value is going to be Vx by 2. And the system is going to finally reach the steady state value from the high frequency value. Again, we have already seen when can you have a response like this. Okay, so if your initial value is greater than the steady state value, then usually there is a 0 and the 0 occurs first, then the pole. Okay, we can say it from that, or this is also a leading phase system. We can best look at the transient response and say that. Okay, I've already discussed what a leading phase system is extensively when we spoke about first order RC circuits. You can go through those lectures. So in another circuit we have one inductor, two resistors, but this also has a 0. Again, we know how to compute the transfer functions, the zeros and the poles. We just did that in the last lecture. So here we will not resort to the transfer function, but directly we will try to plot the response from transient domain, from time domain itself. So the instant you apply the input, inductor behaves like an open circuit. So if the inductor behaves like an open circuit, the circuit simply reduces to, there is no current in the circuit because inductor is an open circuit. So V0 will be equal to Vi. So I'm going to, or the output is going to start at Vx volts. In the steady state, inductor is going to behave like a short circuit. So finally, V0 of infinity is going to be Vx by 2. So in the steady state, it's going to go to Vx by 2. So you're going to decay down like this. Again, in this circuit, we can just write these zeros and poles by inspection. Again, when you see a response like this, it automatically means that there is a 0 on pole in the system. Okay, and we can very easily see that the 0 in the circuit is first by equating this part to 0, you will get 0 as R by L. And to find the pole, again effective resistance seen by the inductance, it's going to be 2R by L. So again 0 comes first, this is the 0, this is the pole, 0 comes first and the pole next. So therefore it is again a leading phase system. So you will start from a higher value and then reach a lower value in the steady state. Now the time constant for this here is L by 2R. Again, we know how to compute the time constant for a first order RL circuit. You just have to find the equivalent resistance seen by the single inductor. If you have just one inductor, you have to just find the equivalent resistance seen by the single inductor, and that's going to give you L upon the equivalent resistance is going to give you a time constant. Again, we will analyze this circuit. The instant you apply the input, what's going to happen, inductor is offering a very large resistance, very large impedance. So I can write the high frequency circuit as, we can ignore the resistors because the impedance of the resistor is much smaller compared to the impedance of the inductor at high frequencies. So I can ignore the resistors and the circuit reduces to this. The gain is 2 by 3. So V naught of 0 is going to be 2 by 3 Vx. Okay. And V naught of infinity is going to be, I'll start with an R. In the steady state, the inductive impedances will be 0. So you will be simply reduced with 2 resistors in a potential divider network. And the gain for this is half. So V naught of infinity is going to be Vx by 2. Again, in this circuit, you are going to start from 2 by 3 Vx and steady state value is Vx by 2. You are going to decay down. And the time constant here, you see this circuit we have already discussed, the current is same in both the inductors, so therefore there is a linear relationship between the voltages. Therefore the order of the system is only 1. Okay, this is 2L. The order of the system is just only 1. Now since it's a first order system, it has a time constant. All you need to do is find the effective inductance, equivalent inductance. Since both the inductors are in series, I can simply add the two inductors, okay, and divided by the equivalent resistance. In this case it is 2R. So that will give you the time constant. Okay, as I said, you can have more and more inductors as long as you have a linear relationship between them. We can actually reduce that to a, even if I have more inductors here, they both are in series, so I can reduce them to a single inductor. Okay, we can also look at it this way. In fact, if I am going to apply a voltage between these two terminals, when I am going to find the effective impedance, it's going to contain only one. It's simply going to contain a term like this, SL dash plus SL equivalent plus R equivalent. From that itself we can get an idea that the current in this circuit, okay, it's going to behave like a first order response. So since it's only containing, there is only a term with S in it, the maximum order of S, the power of S is 1. So therefore from that itself you can conclude that the order is going to be 1. Okay. So again, I'm not explaining this here. It's a leading phase system. There is a 0 in the circuit. So when you look at this time domain response, you should automatically connect that a response like this would automatically imply there is a 0 and a pole in the system. And you should also infer from this graph that the 0 is less than the pole. Okay. The 0 is, you first encounter 0 and the pole. In fact, we can even find the ratio of the pole and 0 by taking out the infinite frequency gain. If you remember from the previous lectures, h of infinity by h of 0 will be omega p by omega z. So you are going to get pole after 0. Okay. So here it will be a factor 2. You can guess all those things by looking at the transient response itself. So that's the whole purpose of this series of lectures, is that you can predict the poles and zeros by looking at the transient responses. Okay. Now in this circuit, again we are giving a step input. You are supposed to find the voltage across the parallel LR network. Now again, I'll need to find the initial response. That is, suddenly when you apply the input, inductor is going to behave like an open circuit. So the circuit will reduce to something like this. It will be an inductor and a resistor, because these two are in parallel. For sudden changes, inductor will behave like an open circuit. So this part will reduce to only a resistor, and this will remain as an inductor. Now for sudden changes, again this inductor is an open circuit. So the current through the resistor is 0. So the output voltage will be 0. In the steady state, here V naught of 0 is 0. In the steady state, the circuit will simply reduce to 2 inductors. Okay, I can ignore the resistor, because when you have an inductor in parallel with the resistor, the low frequency impedance or the DC impedance of an inductor is almost 0. So anything you connect in parallel doesn't matter. So for this the gain is again half. So eventually you are going to reach Vx by 2. and you're going to it's a first order system, so we are again going to reach the final value asymptotically with the time constant given by here. Since there is only one resistor, okay, since there is only one resistor, we can very easily find the time constant as L equivalent by R, the equivalent resistance seen by the equivalent inductance seen by the resistance. So I am shorting the input. If I find between these two terminals, the equivalent inductance is going to be L by 2, so it is L by 2R. Now in this circuit, again we are supposed to draw the step response at the output. So again, first we are going to find V of 0. So for sudden changes, inductor behaves like an open circuit, so the circuit simply reduces to R and R. So I can ignore this part, this arm can be ignored. Okay. Then the circuit is reducing to this, so your V naught of 0 is going to be Vx by 2. In the steady state, inductance will behave like a short circuit. So V naught of infinity is going to be Vx. This effective impedance is going to be R by 2. It will be 2 by 3 Vx. Okay. So your output is going to start from Vx by 2 and eventually go to 2/3 of Vx. Because it's a first order system, there is only one inductor. So to find the time constant here, I have to find the equivalent resistance seen by this inductor. Okay. And that equivalent resistance will be 3 by 2 R. Okay. Or we can actually so what we can do is we can actually short this. There are two ways in which we find. Either you can find the pole. How do you find the pole? You short the input and then equate these two impedances to 0. Negative this impedance here. Okay. So when I short the input, I'll just quickly discuss how to find the time constant. So when you short the input, the circuit reduces to R, and an inductor and an R. So you are supposed to find the equivalent resistance. I'll remove the inductor between these two terminals. So this is R by 2 and that comes in series with R. So you will have 3R by 2. So that's your R equivalent. So once you know the R equivalent, then you can find the time constant as L upon R equivalent, which is 3R by 2. So you have 2 by 3 L by R. Okay. So in fact, this circuit again has a 0 and a pole. By looking at the response, we can say that when there is no initial conditions, when there is if there is a sudden change in the output, it means that there is a 0 for a first order system. Okay. Now whether the 0 occurs first and the pole occurs next, that you can again say from the initial and the steady state values. So in this case, we can say that 0 occurs later, pole occurs first. Okay. So that's why this is actually a lagging phase system. By looking at this response, we can say that. Okay. Yeah, you can easily find poles and zeros by the analysis methods we had used before. Okay. So the pole in this case is going to be 1 by time constant. So that will be simply 3R by 2L. The 0 can be found by equating this impedance to infinity, and that will happen when SL plus R equals minus R. So the 0 is going to be minus 2R by L, or the value of 0 will be 2R by L. Okay, so if you see 0 is 2R by L and the pole is at 1.5 R by L, so pole occurs first. Okay, so with this I think we have the intention of this lecture is to show you how to analyze just by intuition, by inspection, the step response of first order RL circuits. And also we should know when to know that the given circuit is a first order circuit or not. You can have more than one inductor, okay, but still the order of the circuit can be just first order if certain conditions are met. We discussed few examples where such conditions were met. I said if there is a linear relationship between the voltage across inductors, then it can be a first order system. Okay, so using those tricks you can actually reduce the we can very easily guess the outputs of first order RL circuits. So I'll stop at this point.